recapitulate the major point that was discussed yesterday, or rather the problem we had started addressing. We figured out that two problems in kinematics are very important to tackle, and they are the forward and inverse position problems. Later on we'll look at velocities. The way these problems are defined, the forward position problem is to find the positions of the links given the join variables. Of course, the link parameters have to be known, the mechanism parameters have to be known, and the inverse problem is to find out the joined variables which will take the end effector to certain specified positions. So these are the two important problems to be tackled in the controller. So in order to, before we solve that, we need to understand the problem a little better, especially terms like positions and orientations in space. It's fairly easy to understand them in plane. So we need to understand what they mean in space. We also need to understand what is meant by fixed parameters of a mechanism. Again, in a spatial mechanism, you wouldn't have really seen that much. We need to understand this. So we had started out trying to understand what is position and orientation. So that is what we'll cover today. So we had started discussing that. So what is important in specifying position and orientation of a rigid body are not just position and orientation of the rigid body, but rather positions of certain points on the rigid body, on the last body, and maybe directions of certain vectors on that body. If you want to point a gun at somebody, you need to look down the barrel so that that points towards the person or the target, and you are not really interested in any other aspects of the gun, its orientation or position. What you are interested in is that the barrel points towards the target. So what is important to specify depends on the situation or the particular task the robot is carrying out. So we had seen an example where the robot needs to lift this particular part, which is 3 projections, take it to this point and assemble that, push it in basically into these 3 recesses. This requires positioning this part over this part. Now how do you specify it in such a way that the positioning and orientation is precise? In this is a case where, this particular example is a case where you need to position as well as orient the part fully. Right? We'll perhaps see this example in more detail later. Now let us look at what is really required in positioning and orientation. So what we are looking for is the following. So this is essentially what we are looking for. If we say a set of variables specify position and orientation of the rigid body, once the values of those variables are given, we should be able to find out the location of every point of the body as well as the direction of every vector on the body. Then we can say that we have defined the position and orientation of the body. Fine. So we need to find out a set of variables which help us do this, and we need to, using them, determine position of points and also directions of vectors. Right? So let's take what we take a system which we normally use for specifying locations of points. Let's say this is the global reference frame, which one assumes is fixed. So if you take a point P, what we do is the position of that point is specified by the three coordinates xp, yp, zp. So this is a vector of variables which specifies the position of the body. If you are given a vector on a body, so let me draw the body. A vector which we draw on the body, which is attached to the body. Fine. Its direction is given by the direction cosines of that particular vector. Okay. So whatever be the length of the vector, if the direction is what is important, we need to give only the direction vector or the components of the unit vector in that direction. Direction cosines are nothing but components of the unit vector in that direction. So this way, if I call this vector v with an underscore to indicate it's a vector, then the unit vector v cap, the coordinates of that will give us the direction of this vector, which let's say can be written as the x coordinates of that unit vector. So these are things we have already learned. So this is what we mean by finding out position of points and directions of vectors. Fine. Now the problem is the following. Suppose there is a body and we have a global reference frame the body will be moving around in space. Suppose there is a point on the body. How do we specify this is the point that we mean? Because there could be several points on the body, one here, Q here, P here, Q here. Which point are we talking about? Right. So there has to be something with respect to which we define the position of points on the body. Either we mark it, then we can see it while the body moves. So mathematically that is not possible. We need to have a way of specifying that. So what is used is precisely what we had seen. One of the best ways of doing it, there are many ways of doing this, that is essentially locate point on the body itself. You set up a reference frame on the body itself. Let's say I indicate it with small x, small y, small z, the coordinates. So this is a Cartesian reference frame fixed on the body. Now it is easy to say which point you are talking about, right? Now the coordinates of P in the body reference frame, once you give, you know where the coordinates, where the body reference frame is, how it is attached on the body. So points can be specified with respect to that. Same thing, vectors also can be specified with respect to that, right? Exactly the same way we did with respect to the global frame. Fine. These local coordinates, coordinates of points. So I can give it the small x notation. We'll change it a little bit later on. Fine. This is a position of point. This is the local position of the point P. And if you take the vector V, its local direction could be x v cap, small x v cap, small y v cap, and small z v cap. Fine. So we need a scheme basically for locating points and finding out specifying directions of vectors on the body itself, or specifying the vector on the body itself. So now with this we can define what we are talking about. What we are talking about is basically a set of variables, by which a body can be located and oriented, which essentially means that given the values of those variables, we should be able to find out the position of every point on the body and every vector on the body, right? Which means given the location of a point P on the body, xp, yp, zp, this is the local coordinates, we need to find its global coordinates. That is, given xp, yp, zp, the local coordinates, by some means we should be able to find its global coordinates. Fine. Same thing with respect to the direction of vector. Given the local direction of the vector, we need to find out the global directions of that vector. Right? And we are saying that variables which we use in order to help us do this are variables which specify position and orientation of the body, because what these values are would depend on those variables. And what the global location of the point is and the local global direction of the vector is depends on how the body is oriented and how the body is positioned. Right? So this is what we are trying to do. Now this can be done with the three-dimensional geometry that you have learned. Okay, let me first tackle orientation, not orientation but rather how we will transform the direction vectors from local coordinates to global coordinates. So take two reference frames, one global, one local. Now consider a vector in this. So let me give notation. So this is a unit vector whose coordinates in the local frame are known. We need to find out its coordinates in the global reference frame. Okay. So let's assume that the direction cosines of this are these vectors. These vectors, can you see clearly? Not very clear. If I draw the local again larger here, look at the three projections along the three local coordinate directions. Those are the direction cosines of this vector, or this being a unit vector, they are nothing but the coordinates of the vector. Fine. So this is this particular the length of this particular vector is small x v cap, right? That is how we give the notation. Small y v cap and small z v cap. So we know this. We need to find out the global coordinates of this. That is essentially obtained by transferring this vector here and projecting it along the global axis directions, and those coordinates are the global coordinates of that vector. Fine. Now we can do the following. These vectors which I have drawn here, or rather which are there here, are vectors in this global coordinate frame, right? And the sum gives you the total vector v cap, correct? So if I am able to express these vectors, this small x, small y, small z, or rather this xv, the vector with length xv in this direction, yv in this direction, zv in this direction, and sum them up, then I get the global coordinates of that vector, that is x v cap, y v cap, z v cap. Okay. So I can write this in the following way. Look at unit vectors in the direction of the local axis. That multiplied by these lengths x v cap, y v cap and z v cap are the three vectors I am talking about, right? Sum them up. So let me call the unit vector in the x direction as x cap. Fine. Multiply it with this length, which is x v cap, you get this vector. Fine. Similarly, y cap, the unit vector in the local y direction, into y v cap, which is the length of the vector, plus so all of you agree with this, right? I can put it in symbol matrix form to make the notation more compact as follows. This is one column, this is another column, this is the third column. Each of them are three-dimensional vectors. These are the unit vectors expressed in the global frame of the local frame directions. And then I put all this into a vector. I have x v cap, y v cap, z v cap. If you remember, this is nothing but the direction of the vector v in the local frame. This vector is nothing but the local frame vector v cap. Fine, and this is nothing but the global frame vector v cap. So we have a matrix which pre-multiplies it to give you this transformation. And the elements of this matrix are the unit vectors in the directions of the local coordinates expressed in the global frame. So let me give a notation for that. So this is the vector x cap, which is a unit vector in the local x direction, and its components in the global x, y and z directions. So similarly, multiplied by this local vector, so this is a matrix which transforms a unit vector in the local reference frame to a unit vector in the global reference frame, and these really needn't be unit vectors, they can be vectors of any size. So they are essentially free vectors, that is what is more important. So and they are essentially free vectors. Now this particular matrix is called the rotation matrix and given the notation R, because this captures all the information about orientation. Why it is called rotation, I will come to a little later. We will for the moment call it orientation matrix, and this takes a vector in the local frame to vector in the global frame, which is given notation like L to G, L as a suffix on the right hand side and G as a suffix on the superscript on the left hand side. This is a matrix. What is the size of the matrix? 3 by 3, right? So this transforms a vector. Now it needn't be a unit vector, can be any vector, but it's a free vector. So I'll say that this is in the local frame with this subscript L. So you get the vector in the global frame. The curly brackets typically for vectors and square brackets typically for matrices. Fine, this is fairly clear. Later we will see that this particular matrix is what is, and this particular matrix has been able to give you the directions of vector in the global frame once it is given in the local frame, and this turns out to be, this is called the rotation matrix. So let us look at the elements of the rotation matrix in a little more detail. Any questions here? It is simply addition of some vectors to give you the global vector. That is how we derive the transformation. So what is important are these elements. Now looking at the elements here itself, we should be able to note a few very important facts about these elements. I said that these particular vectors, column vectors, are the vectors, unit vectors in the directions of the local axis. So any two such columns are orthogonal. Fine, that's straightforward. And also each of them is a unit vector. Fine. So such a matrix is called an orthonormal matrix. such a matrix is called an orthonormal matrix. I'll, because of some of these things which I said about orthogonality and length being unity, it turns out that these 9 elements are not independent. Right? They are more than what you really require to do this transformation, but it is very convenient to use them. We'll see these points a little later. Now let's look at typically what numerical values. Yeah. We did not, but if for yeah. Yeah, actually, this is related to the concept of free vectors which I mentioned. So, I'll state the question that he asked and clarify that, because in the camera it will not be captured what you asked. Fine. What Himanshu is asking is essentially this. So, you have a global frame. And you have some body to which you attach some local frame. Let's say x, y, z. Suppose there is a point here and its vector in the local frame is this. The vector which defines the position of that point in the global frame is this. Right? So if this turns out to be unit, let me call this point as A. If this vector AP is the unit vector, it will no longer be the unit vector here. Right? That is the question that you asked. Or something else. Right, right. Yeah. No, it is fully reflected actually. Only thing, the problem I am solving is not this. This is what I am going to come to. This is the problem of finding the position of a point in the local frame, the position of that point in the global frame given its position in the local frame. So imagine that there is some point in space and you express the position of that point with respect to the local frame. You want to find out the coordinates of that point in the local frame. So we are looking at coordinates of points. The transformation that I just now talked about are transformations of free vectors. Fine. So take this vector which is there in the local frame. I am transposing this to this particular origin, bringing it here. I am trying to derive the coordinates of this vector in the global frame, or rather this particular point. Once you transpose it like this, it becomes the coordinates of that point. So these are free vectors which you can translate whatever way you want. What I am expressing is the direction and magnitude of the vector, not the location of the point at which the tip of the vector turns out to be if I place the vector somewhere. Fine. So these are two different things. Fine. So what happens is that if I multiply this with 2, this also gets multiplied by 2. So that is captured here. When V is doubled, Vg also will be doubled. Fine, that point is clear. Okay, now let us look at a typical typical transformation. How does it look like? So let this be x, let this be y, global, and let this be the local frame, x, y, small x, small y. So this has been rotated by some angle theta. The origins are coinciding, and I have rotated the so origins are coinciding, and initially the local frame is aligned with the global frame. I then rotate the local frame with respect to the global frame about the z axis. Fine. So z axis coincides still, they are aligned still. X and y axis are not aligned. Fine. So now let us try to write this matrix L with respect to global. What do you think would be the elements? So if you remember, if you look at your notes, this particular column is the coordinates of the unit vector along the local x axis. Now if you look at each of them, these are, you also know that these are direction cosines being unit vectors. So each of them, if you look at it, is the cosine of the angle between the global x axis and the local x axis, cosine of the angle between the global y axis and the local x axis, cosine of the angle between the local global z axis and the local x axis. That's what it is. Fine. So having done the rotation the way we just now saw, we can write down the coordinates very easily. Look at the unit vector along this direction. Along the global x direction, it will have cos theta as the component, right? Along the local y axis, it will have sin theta as the component. Fine. And what about the global z axis? What is the component of 0? Similarly, the unit vector along y, what are its components in the global reference frame? Minus sin theta, then cos theta, 0. Z is out of the plane, right? So the components of local z with respect to the global frame, no, the entire vector 0, 0, 1, right? So this is exactly what a rotation matrix will look like if the local frame is oriented with respect to the global frame in this fashion. Okay, we will come to more complex orientations a little later. I just wanted to show you an example. Now let us look at the next point, which is given the position of a point in the local frame, we want its position in the global frame. So let's do that. Don't worry about these lines I am drawing. This is to ensure that the lines don't get mixed up. Later on you can draw things. So I have the local frame here, as I have shown, the global frame here. there is this particular point Q on the body. Right? The origin of the local frame is P. So the vector PQ is known in the local frame. I want the position of Q in the global frame. The position of Q in the global frame is this vector. Let me call the origin of the global frame as O. Right? So what we want, that is the global coordinates of the vector of the point Q. Our notation for that was this, I suppose. This is what we want. This is the sum of these two vectors, OP and PQ. And these are vectors which are expressed in the global frame, remember. Fine. So now look at this vector PQ. If I can get the global, if I know the local coordinates of the vector PQ, I can do the transformation which I just showed in order to get its global coordinates. Right? So I can write this as OP plus the rotation matrix from local to global multiplying the local coordinates of PQ. Fine. So now this can be written as OP is the position of P in the global frame, which our notation for that is capital XP, capital YP, capital ZP. That is the origin of the local frame in the global reference frame, plus this rotation matrix from local to global into multiplying the local reference, local coordinates of the point Q, because P is the origin of the local frame. So this is nothing, this vector is nothing but the local coordinates of the point Q, right? So that is small x Q, small y Q, small z. Fine. This operation transforms points on the local reference frame which is attached to the body. So points on the body to their locations in the global reference frame. So this is what we set out to do, right? So what are the variables that we use to do this? This is what the variables we use to do this is what we defined, what we said are those that specify the position and orientation of the body, because when the body moves, these variables change. And with these variables, you can always find out the location of points on the body in the global frame. Right? So what are those variables now? Right, elements of this matrix, 9 of them, right, and elements of this vector, 3 of them, correct? That is what helps you transform the points on the local frame to the global frame. What about the transformation of free vectors in the local frame to global frame? What is required for that? Just this matrix, right? So So one way of doing it, this is not the only way, this is a very convenient way, and we will be using this mainly. But one way of specifying position and orientation of rigid bodies is to give these two vectors one position of origin of local frame. So this is in the global frame. And the other is this rotation matrix, local with respect to global. So these two things taken together specify position and orientation of rigid bodies. And with this we are able to do what is important for us, which is specify directions of vectors and locate positions of points. Okay. Now look at this a little bit. Suppose I fix this. Fine. Imagine that the body is like this and the global frame is like this, and we have got these matrices and vectors. Now I am going to fix this, and then I am going to vary this vector, allow it to change. What happens to the body? Right? It purely translates with the orientation which is already given to it by this particular specification fixed. Okay. What does it mean? It means that this particular matrix is able to fix the orientation. Okay. And now look at it the other way. I fix this and I change the elements of this matrix with the constraint that the columns are unit vectors and it is orthonormal, with the constraint that it remains orthonormal. Fine. In addition, there has to be one more constraint, but let me say it remains orthonormal. What happens to the body? It rotates, but it has a special type of rotation. It rotates about a point, the point P. Right? So when I fix this and when I change this, it rotates about the point P. Right? So another reason why it's called the rotation matrix. Now let us consider the following. What happens to points on the body and vectors on the body when we do this? Okay. So imagine I am fixing this and I am changing this. The body translates. What happens to points on the body? They move with the body. Right? They move with the body with respect to the global frame. Okay. What about vectors fixed to the body? They move parallelly, the directions don't change. So directions of the vectors don't change. That is precisely the definition of translation. That's why some of you immediately said it's translating. Okay. Now what about the other thing? I fix this and change this. What happens to vectors? The directions change. Right? What about points? Except for P, everybody else changes. Right? So this you have to keep in mind, that when I change the rotation matrix, the directions of vectors as well as positions of points change. Whereas when I fix this and change this alone, the positions of points change but directions of vectors don't change. Okay. So this basically, if you fix this, then the body translates when you change this, and if you fix this and change this, the body rotates about the point P. That is why it's called the rotation matrix. Now this is not the only way we can get this particular transformation of global local locations of points to its global location, and local directions of vectors to its global direction. This is not the only way we can specify we can get this transformation, or this is not the only way we can specify position and orientation of rigid bodies. So I'll just list down a few more alternatives. You can see why they are equivalent. All of them will be able to give you the same thing. So one is positions of three non-collinear points. So on the body, mark 3 points. Shouldn't be on a straight line. These 3 points shouldn't be on a straight line. Now if you give the location of these 3 points in the global frame, that by itself defines the position and orientation of the rigid body. What it really means is that it fixes the rigid body in a particular position and orientation in the global frame. Fine. So how it is possible now to transform points and vectors in the local frame or in the on the body to the global frame is something you will have to figure out. Okay. Now another possibility is positions of 2 points non-collinear points on the body, I'll say. So mark 2 points on the body, mark a vector on the body which is not along parallel to the line between the 2 points. Yeah. Not really. So the question asked was, don't you need one more point? This being a 3-dimensional body, 3 points always lie on a plane. So this appears to specify the location of a rigid body which is planar, right? Don't you need a fourth point which is not in this plane? The answer is no, you don't need it. So you should figure out why it is so. Yeah, but that is already given by these 3 points. Since you have a plane, you know the normal to the plane, right? Yeah. So you can still a plane could have orientation based on the 3 points that you have specified. You can find out an orientation. So these are definitely questions that you should ask. So in the process of trying to figure out how you can transform points, you will be able to figure out why it is possible, why this is fine. Okay, I would like you to go through that exercise. So treat this as exercises, how you will do the transformation if you have this. Basically all you have to do is convert this to what you already know into the picture of the reference frame. If you are able to do that, then immediately you can do the transformation through that route. Okay, so this is another alternative. Another is position of 1 point. So So it's all on the body, the vectors and points are on the body. All these are equally good in the sense they will do the job. Maybe a little more difficult to do the job with them. The job is that of transforming vectors and points. Fine. And you could figure out other ways of doing it also. Now, suppose you have a body here to which you have attached a reference frame, and you have another body on which there is another reference frame that is attached, and now you have the global frame. Now I'll slightly change notation and call this x1, y1, z1, because there are more than two bodies. So x2, y2, z2, let's say z3, x3, y3. Suppose you know the position and orientation of this body with respect to this and this body with respect to this. Can you find out the position and orientation of this body with respect to this? Fine. This is an important question. This is so important that in most of our forward and inverse kinematics we will use this. Okay. So position of this body with respect to this, what does it mean? It is the position of this point with respect to in this coordinate frame, and the rotation matrix transforming vectors in 3, free vectors in 3 to 2, right? So let us write it down. So let's also call this as, let's say, O1, O2, and this is O3. Fine. So position and orientation of body 3 with respect to 3 is given by the vector O3. So let me write it as a vector. So O3 is a vector expressed in the second reference frame. Sorry, O2, O3 I should have considered. So O3 is the point O3 expressed in the second reference frame, and the rotation matrix 3 with respect to 2. This is the position and orientation of this body with respect to this. Okay, and we have the position and orientation of this body with respect to this, which is O2 expressed in the first reference frame, and the rotation matrix from 2 to 1. Fine. And from this we should be able to calculate what? O3 in this reference frame, that is the position and orientation of this body in this body, that is O3 in reference frame 1 and rotation matrix 3 with respect to 1. One way this can be done is to look at transformation of points in 3 with respect to 1. Right? So take a point here, P. So try to find out its position with respect to 1. So that is x sorry, xp, yp, zp in reference frame 1. Fine, is equal to how do you specify that? So location of this particular point could be made up of a vector from here to here and a vector from here to here, right? So let me call it O1, O2, that segment in 1, fine, plus this particular segment O2, O3 again in 1, right? Or let me not do that. I'll consider this particular vector O2 P. So instead of O3, let me use P. Fine. So this is P in 1. Okay, O2 P in 1. So I can write it as follows: O2 with respect to O1, fine, is already given, correct? So O2 in 1 plus this P with respect to O2. Now we can use this transformation. We can use the position of this position and orientation of this body with respect to this body to find out the position of P in this reference frame. That is, and then we can one moment. This, okay, this is this vector. This is this vector in. If we consider this vector in the second reference frame, we can transform it to the first reference frame. Right? These are considering it as a free vector. So what do we get? We have R2 with respect to 1 multiplying position of P in this reference frame. That is xp, yp, zp in reference frame 2. Fine. So let us explain further. Now look at this vector position of P in the second reference frame. We can express it in terms of its position in the third reference frame, correct? So that involves what? O3 in the second reference frame. So that is known, right? That is known, plus rotation matrix 3 with respect to 2 multiplying the position of P in the third reference frame, right? So xp, yp, zp okay. What we have done is we have put all this in terms of what we know. Okay, so now if you expand and simplify, yeah, oh, this, yeah, you should give me a warning. Yeah. So what we have done is understand one way of specifying position and orientation of rigid bodies and see how we can transform points and vectors from one to another. That is essentially what we have seen. So remaining we will see in the next class. Thank you.